All right, let's get started. Welcome, everybody. Before I introduce today's speaker, let me mention a couple of things as usual. So the video recordings of the talk from last week by Alexandra Holpke and the talk from the week before by Tatiana Nagnibeda are available at the seminar webpage. So you're welcome to view them. We do have one more talk scheduled this semester next week by Benson Farb next Thursday. So the information about his talk is already available at the seminar webpage. And today, after the talk, you're very welcome to hang around for a little longer. So after we stop recording, we'll have a slightly more extended chat session so for people to talk more informally. So with that said, I'm pleased to introduce today's speaker in the New York Group Theory Seminar. It's Emily Stark from the University of Utah, and she's going to tell us something about action rigidity for free products of hyperbolic manifold groups.
All right, thank you very much for the invitation. It's nice to see you. So today I'll discuss rigidity that can manifest when two groups act geometrically on the same space. And this is joint work with Daniel Woodhouse. So to start with the definitions, we say that model geometry for a group G is a proper geodesic metric space on which the group G acts geometrically, meaning properly and co-compactly by isometries. So for example, every finitely generated group admits infinitely many model geometries. The group G acts geometrically on any Cayley graph constructed with respect to a finite generating set. As a special case relevant to this talk, the free group, denoted Fn, acts geometrically on a bounded valence tree. And a third example relevant to this talk, the fundamental group of any closed hyperbolic n-manifold acts geometrically on hyperbolic n-space. So each of these actions is geometric, and all of these spaces are model geometries for the corresponding groups. So one main aim of geometric group theory asks to relate the following three notions and their relationships. So let me write them to refer back. So we're first interested in understanding when groups G and G prime have a common model geometry, meaning that the groups G and G prime both act geometrically on the same proper geodesic metric space. Then by the Milnor-Schwarz lemma, this implies that the groups G and G prime are quasi-isometric, meaning that they have the same large-scale geometry, and are interested in understanding when the converse holds. When does this geometric equivalence, or when can this geometric equivalence be realized through group actions on the same space? The third notion we're interested in is algebraic. We say that groups G and G prime are abstractly commensurable if they contain finite index subgroups H in G and H prime in G prime that are isomorphic. And since any finitely generated group is quasi-isometric to any of its finite index subgroups, if the groups G and G prime are abstractly commensurable, then they are quasi-isometric. The other four implications missing in this diagram don't hold in general, and I'll give examples in this talk. But first, there are two important rigidity phenomenon that can be illustrated in this diagram. The first is the notion of quasi-isometric rigidity. So we say that a group G is quasi-isometrically rigid if whenever G prime is a group that is quasi-isometric to G, that implies the groups G and G prime are abstractly commensurable. And the existence of this implication is what we call action rigidity. So we say a group G is action rigid if whenever G prime is a group that shares a common model geometry with G, that implies the groups G and G prime are abstractly commensurable. So in both cases, algebraic information is deduced from some geometric information. And if a group is quasi-isometrically rigid, it's automatically action rigid by Milner-Schwartz.
So maybe a stupid question, but still, there is another common way of producing quasi-symmetric groups where you mod out finite normal subgroups. So you don't have to worry about this here in this discussion, or.
So here we will actually show that the groups have isomorphic finite index subgroups without modding it.
Right. Because I don't remember. In general, it might not be true, is it? I can't remember now that if you have a group that has some finite normal subgroup, you quotient it out. Is it?
Like sometimes I've heard that referred to as virtually isomorphic. And
right. So that doesn't apply abstract commensurability, does it?
In general, no, I think no. I don't have an example on my mind.
Okay. All right. Thank you.
Okay. So let me first start with two classic examples. First, hyperbolic manifold groups. So the situation is special in dimension 2. So first consider the class of groups that act on the hyperbolic plane geometrically. Then by definition, there's one common model geometry for all groups in this class. They act on the hyperbolic plane. And therefore there's one quasi-isometry class. And in dimension 2, there's also one abstract commensurability class. The situation changes in higher dimensions. So if you consider the groups that act on hyperbolic n space geometrically for some fixed n at least 3, then as before, all groups in this class have a common model geometry, hyperbolic n space. So there's one quasi-isometry class. However, there are infinitely many abstract commensurability classes, and the invariants are number theoretic. So groups in the class B give examples of groups that are quasi-isometric, but are not abstractly commensurable, and give examples of groups that have a common model geometry, but are not abstractly commensurable. So in other words, the fundamental group of a closed hyperbolic n manifold for n at least 3 is not a quasi-isometrically rigid group, and it's not an action rigid group. As a second class of examples, consider the following virtually free groups. Let GP be the free product of the finite cyclic group Z mod P to Z with itself, where P is some prime at least 3. Then these groups are virtually free. They contain a free group as a finite index subgroup. And therefore, there's a single quasi-isometry class and a single abstract commensurability class within this set of virtually free groups. However, work of Mosher, Segev, and White prove that the groups GP and GQ have a common model geometry if and only if P is equal to Q. So two of these virtually free groups act on the same metric space if and only if they're isomorphic. And so their work give the first examples of groups that are quasi-isometric, but do not have a common model geometry, and groups that are abstractly commensurable, but do not have a common model geometry. And to make two remarks about this result of Mosher, Segev, and White. So the first is that the obstruction to having a common model geometry disappears after passing to a finite index subgroup. These groups are virtually free, so they have finite index subgroups that have a common model geometry. And the second remark is about the proof of this theorem of Mosher, Sieve, and White. The main deep work in their proof is to show that if two of these virtually free groups act on the same proper geodesic metric space, then they actually act on the same tree geometrically. But the only tree that the group GP can act on geometrically is the Basser tree associated to this splitting. So it's the only tree GP can act on is the p-valent tree, p-regular tree, and likewise for GQ. So the I guess the takeaway, because it's relevant for our theorem too, is that the first big step in the proof is to promote the common model geometry to a much nicer one. Okay. So we are interested in kind of a hybrid of the previous two classes of examples. We consider free products of the following form. So let C be the set of free products of groups H1 through HK with possibly a free group, Fn, where K is at least 2 and N is greater than or equal to 0. So there may or may not be a free piece. And each group, HI, is the fundamental group of some closed hyperbolic Ni manifold for Ni at least 2. So there's a picture. It's the fundamental group of some space built out of manifolds and a graph. And to remark, our results hold for uniform lattices in the isometric group of a rank 1 symmetric space in more generality. So the real hyperbolic manifold isn't important, and these groups don't need to be manifold groups. Torsion's also fine. Okay, so the quasi-isometry classification within this class of free products follows from work of Papasoglu and White from 2002 in much greater generality. But in this specific case, it says that two free products of hyperbolic manifold groups, G and G prime, are quasi-isometric if and only if the quasi-isometry types of their one-ended factors agree, ignoring multiplicity. So as shown in the picture, all that matters is the set of dimensions of the manifolds in the free product. It doesn't matter how many of each dimension, as long as the set of dimension numbers match. These groups are quasi-isometric. So the moral of their theorem is that quasi-isometries between free products are very flexible. It depends only on the one-ended factors, the quasi-isometry types of the one-ended factors. So in contrast, for free products of hyperbolic manifold groups, within every quasi-isometry class, there are infinitely many abstract commensurability classes. And this follows from classic results if there's a manifold of dimension at least 3, and if all of the factors are surface groups, this follows from work of White. So in other words, every free product of hyperbolic manifold groups is not a quasi-isometrically rigid group. There are groups that are quasi-isometric to it, but are not abstractly commensurable to it. So in contrast, we prove that these groups are very rigid if you actually want them to act on the same space. So our theorem shows that every free product of closed hyperbolic manifold groups is action rigid. So just to recall, that means if you have any group G prime, so that G and G prime act geometrically on the same space, that automatically implies the groups G and G prime are abstractly commensurable. And as a consequence, we have the first examples of the following. There are quasi-isometric groups that do not virtually have a common model geometry. Since the class of free products of manifold groups is closed up to passing to finite index subgroups, this obstruction can't disappear after passing to a finite index subgroup. we have, we found additional rigidity if the free product in question contains exactly 2 factors and both of those factors are surface groups. So suppose you have 2 free products, G and G prime, 2 free products of fundamental groups of closed hyperbolic surfaces. Then the groups G and G prime have a common model geometry if and only if they're isomorphic. And as a consequence, we have the first examples of the following. There are torsion-free, abstractly commensurable groups that do not have a common model geometry. So in other words, the relation of having a common model geometry is not transitive, even among torsion-free groups. And I should say that our first theorem is an example of a class of groups where the converse to Milnor-Schwarz fails in a very big way. It doesn't disappear in passing through finite index groups. Okay, so to give an example of the corollary, if you have 2 free products of surface groups, then White proved that those groups are abstractly commensurable if and only if the groups have the same Euler characteristic. So for example, the fundamental group of the free product of surface groups of genus 3 and the fundamental group of the wedge product of the surface of genus 2 with the surface of genus 4 are abstractly commensurable, but those groups cannot act on the same proper geodesic metric space because they're not isomorphic. Okay, so before explaining what goes into the proof of those theorems, let me say 2 open questions that we're very interested in. So suppose that H and H prime are one-ended hyperbolic groups. Then the first question is the free product of H with H prime action rigid? So if, in other words, if there's any group G that acts on the same space as the free product H and H prime, does that imply the groups G and this free product are abstractly commensurable? We don't know. And the second related question asks if you have 2 one-ended hyperbolic groups that act geometrically on the same simplicial complex, are the groups H and H prime abstractly commensurable? So in our work, we know the answer if H and H prime are closed hyperbolic manifold groups, but it's very open in general. And to remark, you need the hyperbolicity assumption for both questions, or it's false without the hyperbolicity assumption because of the work of Berger and Moses, who found simple groups that act on the product of 2 trees. Okay, so let me explain what goes into the proof of these theorems. So the strategy has 2 main steps. The first step is, in analogy to the work of Mosher, Segev, and White, we want to promote the common model geometry. So the setup is, you have 2 groups, G and G prime, that are free products of closed hyperbolic manifold groups, and assume that they act geometrically on some proper geodesic metric space X. And so our goal is to show that the groups G and G prime are abstractly commensurable. And the first step of the proof is to show that if G and G prime act on some arbitrary proper geodesic metric space, then in fact they both act geometrically on an ideal model geometry that's built out of copies of hyperbolic n space of varying dimensions and trees glued to each other along intervals and points. So this is the natural model geometry for one of these groups, and you can show that they both act on this very nice ideal space. So why is this helpful? The reason it's helpful for us is that we can now reformulate our goal being that these groups are abstractly commensurable, in topological terms. So the picture is we have G and G prime acting on this ideal model geometry, and suppose they're torsion-free, G and G prime are torsion-free, then the quotient spaces, Y mod G and Y mod G prime, are compact graphs of spaces that are with vertex spaces that are closed hyperbolic manifolds or points, and these are glued to each other along intervals. So these spaces are much nicer than some arbitrary quotient spaces.
Sorry, a quick question here. Can you say something about how you produce this space Y? Are you using boundary considerations or?
Yes, thank you. Yes, so that's a good question. So I will, my plan was to outline the.
Oh, sorry, you're going to tell us later, right? Okay.
Yeah, just come back to the construction of Y.
Okay, very good, thank you.
And we do use the boundary. Okay, so once we've found the space Y, and I'll explain the construction a little later in the talk, we have these two very nice quotient spaces, and now our goal is to find homeomorphic finite sheeted covering spaces of these two quotients. So once you find homeomorphic finite sheeted covers, you get your isomorphic finite index subgroups. Okay, so what is the difficulty in achieving this goal? There are sort of two opposing forces going on in this construction. On the one hand, suppose in these quotient spaces that every manifold was collapsed to a point. So your two quotients are now, suppose, just finite graphs. Finite graphs that have isomorphic universal covers. Then Leighton's theorem proves that there exist homeomorphic finite sheeted covers. That is, Leighton's theorem says that two graphs with isomorphic universal covers have homeomorphic finite sheeted covers. So if there were no manifolds at all, it was just a point, we would be done. But on the other hand, if the quotient spaces Y mod G and Y mod G prime were just a single n manifolds with isometric universal covers, then in general, it would be impossible to find homeomorphic finite sheeted covers because there are incommensurable hyperbolic n manifolds for n at least 3. So our result shows that the situation of a graph of manifolds is much more closely related to the graph case than to the manifold case. Okay, so let me say what goes into proving the existence of this of these homeomorphic finite sheeted covers. So the main tool we use in the end is a souped up version of Leighton's theorem that was recently proven. So before I write the souped up version, let me rephrase Leighton's theorem. So Leighton's theorem says that two graphs with isomorphic universal covers have isomorphic finite sheeted covers. Or alternatively, you can say that free uniform lattices in the automorphism group of a bounded valence tree are commensurable inside the automorphism group of the bounded valence tree. And so Leighton's theorem in that wording says the following. So the symmetry restricted Leighton's theorem, which is what we use, was recently proven by Gardam and Woodhouse and independently by Shepard. And like Leighton's theorem, it proves that free uniform lattices in the automorphism group of a bounded valence tree, T, so that the lattices are contained in symmetry-restricted subgroups, a symmetry-restricted subgroup H in the automorphism group of the tree, are commensurable within this symmetry-restricted subgroup H. So as one example, you could imagine that your graphs are colored and your tree is colored, and H is the color preserving automorphism group of the tree. That's one example. So symmetry restricted Leighton's theorem recovers the result that if you have two colored graphs with isomorphic colored universal covers, then they have isomorphic colored finite sheeted covers. So this symmetry restricted, it doesn't have a clean description, but we can talk about it if people have questions. But it lets you add extra structure to the graph that you want to preserve when passing to the finite sheeted cover. And that's really useful for us because we need to keep track of the dimension and commensurability class of the pieces in this graph of manifolds. So the ultimate step in our proof is to apply the symmetry-restricted Leighton's theorem. And the difficulty from our point of view is actually setting up the framework to apply this theorem, because it applies to free uniform lattices in the automorphism group of a bounded valence tree. And we naturally have two groups that are acting on the dual tree to this ideal graph of spaces, but the groups aren't free and the tree is not bounded valence. So the work in our result is to reduce to the case that you can actually apply symmetry-restricted Leighton's theorem and find commensurability. Okay, so for the remainder of the talk, let me explain the construction of the ideal model geometry. It comes from the main, the theorem behind the ideal model geometry is the following. So suppose that G and G prime are hyperbolic, infinite-ended, and not virtually free groups. So this includes the class of groups we're interested in, where the one-ended pieces are manifold groups, but this theorem holds a more generality. And suppose that the groups G and G prime act geometrically on a proper geodesic metric space, meaning they have a common model geometry. Then the groups G and G prime act geometrically on a simply connected simplicial complex. So you can promote the model geometry to a simplicial complex. And in addition, this complex has a tree of spaces decomposition, where the vertex spaces are either one-ended or a point, and edge spaces are intervals. Okay, so for experts, the difficulty in proving this theorem, or the real thing that we show, is that you can show that the groups G and G prime act on the same simplicial complex. That's what's new. And then you can apply the work of the Rips construction to find a simply connected simplicial complex. And then you can apply Dunwoody's tracks to get the tree of spaces decomposition. So really what we show is that they act on the same simplicial complex. And then the rest follows from classic geometric group theory results. Okay, so a few remarks on the three hypotheses on the groups G and G prime before I explain how you build a simplicial complex. So the first remark is that this case that the groups G and G prime are virtually free is due to the work of Mosher, Segev, and White. They proved if two virtually free groups act on the same space, then they actually act on the same tree. So that case is Handvolt. In general, the result is false if the group G is one-ended. For example, you can show that the fundamental group of incommensurable, hyperbolic, and manifolds cannot act on the same simplicial complex. So infinite-ended is needed in general. And the hyperbolicity assumption, in current work in progress with Sam Shepard and Daniel Woodhouse, we can remove the hyperbolicity assumption. We're trying to prove action or rigidity outside the hyperbolic setting, and we believe we have a stronger version of this theorem.
So how would it sound if you remove the hyperbolicity assumption?
We think the same. We think you might need finitely presented.
Just finitely presented, infinite-ended, and not virtually free.
Yeah, because you need something simply connected in order to apply Dunwoody's tracks. You need simply connected to a skeleton.
Okay, thanks.
Okay. Okay, so let me explain. In the hyperbolic case, how do you build a simplicial complex? The idea is to use the structure of the visual boundary of a free product of hyperbolic groups. So as set up, suppose that G and G prime are free products of one-ended hyperbolic groups, HI and HI prime. And suppose that the groups G and G prime act geometrically on the same proper geodesic metric space X. Then the visual boundary of G is homeomorphic to the visual boundary of G prime, which is homeomorphic to the visual boundary of X. Okay, and an example to keep in mind is if the group G is the free product of two surface groups, then it's acting on the universal cover, which is built out of copies of the hyperbolic plane glued to each other along intervals. And there's a dual tree associated to the universal cover where every hyperbolic plane has been collapsed to a point. And work of Martin and Swiatkowski describes in detail the topology of a free product of hyperbolic groups, and in particular, as a set, the visual boundary of the space X can be written as a disjoint union of components of two different types. So first, there are atomic components, which correspond to the ends of the tree T. Those are geodesic rays in the space X that leave every vertex space. Those are singletons in the boundary. And the other components in the boundary are called non-atomic. And there's one component for every coset or conjugate of a one-ended vertex group. So in this example of these surface groups, the non-atomic components are exactly the circles that arise as boundaries of copies of the hyperbolic plane. Okay, so this just records the setup from before. We have G is the free products, and its boundary has this decomposition into two types of components. So we want to build a simplicial complex from this data, and we need one other definition first. So for every non-atomic component in the visual boundary, so in this example, a non-atomic component is just a circle. We let X sub alpha be the weak convex hull of the set S sub alpha in the boundary, where the weak convex hull is by definition the set of geodesics in the space X that have both endpoints in the subset S sub alpha in the boundary. So in our example, the weak convex hull of one of these circles just recovers the hyperbolic plane, but in some arbitrary proper geodesic metric space, the weak convex hull could be more complicated, although Swenson proved that for hyperbolic groups, these weak convex hulls are quasi-isometric to the stabilizer of S sub alpha inside of G. Okay, so our strategy is to build some simplicial complex for every weak convex hull, so one for each component in the boundary, and then glue them together if they're close. Okay, so to say a little bit more precisely, this just carries over the notation from before. We have a free product acting on some space X, and we take some component, S sub alpha in the boundary that's non-atomic, it's not a singleton, and we let X sub alpha be its weak convex hull. And we want to replace the weak convex hull with a simplicial complex. Okay, so sorry for a little more notation, but we do the following. Let U alpha beta be the intersection of the space X sub alpha with the R neighborhood of X sub beta. So you take neighborhoods of the weak convex hull X sub beta until it intersects X sub alpha. And if there's non-empty intersection, that set is called U alpha beta. And we want to take these neighborhoods big enough so that the weak convex hull X sub alpha is fully covered by these U alpha beta, covered by neighborhoods of its sort of neighboring weak convex hulls. Then the simplicial complex for the weak convex hull X sub alpha is just the nerve of this cover. There is one vertex for each set U alpha beta, and they're connected by an edge if the two sets intersect. And you can prove that this nerve is quasi-isometric to the to the weak convex hull X of alpha. So we're going to replace X alpha with this simplicial complex. And you can do this for each non-atomic component in the boundary. Each circle gives you a weak convex hull, and you can build a simplicial complex in this way. And there's a natural way to connect to simplicial complexes. So if the R neighborhood of X beta intersects X alpha, then the R neighborhood of X alpha intersects X beta. So if that happens, then you connect the two corresponding vertices with an edge. And this gives you a big simplicial complex. And since it's constructed within the space X and using the boundary, which both G and G prime act on, the groups G and G prime act on this simplicial complex, and you can show they both act geometrically on this simplicial complex. And you can see from this construction how important it was to have a free product. It's really using the free product structure, or an infinite-ended structure. Okay, so that's how we build a free product. That's how we build a simplicial complex for infinite-ended hyperbolic groups. And in our special case, we want to obtain this ideal model geometry. And so if we have free products of hyperbolic manifold groups, then we apply the work of Tulkia, Hinkanen, Markovich, Chow, and Pamsu, depending on the rank 1 symmetric space, to replace these one-ended vertex spaces equivariantly with copies of some hyperbolic space. Okay, so thank you. That went a little fast. So yeah, I guess I could say one other thing. So in current work with Sam Shepard and Daniel Woodhouse, we're trying to extend this to non-uniform lattices in isometry groups of rank 1 symmetric spaces, uniform lattices in isometry groups of higher rank symmetric spaces, and a few other classes. We're trying to find the right generality outside the hyperbolic setting.
All right, okay, thank you very much. Let's thank Emily. Okay, so now if there are any questions, you're welcome to ask them. And you can unmute yourself when you do that.
So you said that it's an open problem if you have two one-ended hyperbolic groups, whether the free product is action rigid, right?
Mm-hmm.
So is it like known with some restriction on the groups, for example, if the surface groups or something like this?
Wait, say that one more time. Sorry.
Okay, so this question, so is the free product of two one-ended hyperbolic groups is action rigid? So my question is it known that such a free product is action rigid under some restrictions on this hyperbolic group?
So I think for groups that are not, generally I think no. These questions are pretty like untapped. I know that Woodhouse and Shepard have some work in progress, but in general, for classes of groups that are not quasi-isometrically rigid, I know only 3 examples of groups that are action rigid. This result, the work of Mosher, Skiv, and White, and earlier work with Woodhouse on surface amalgams, simple surface amalgams.
Surface amalgams. So if you have, for example, 2 closed surface groups and you take the free product, it is action rigid.
The free product, we don't.
Of 2 closed surface groups. Suppose you have 2 closed surface two hyperbolic surface groups closed, so they are one-ended, and take their free product. So is it action rigid?
Yes.
Yeah, this is the main result of.
Yeah, that's one of the main results. Yes.
But you also have when you amalgamate along a curve, right? For the
Yes.
surface group.
Mm-hmm.
What about in general if you have like a JSJ decomposition? So like that's kind of like a graph. You can make like a graph of spaces or something. Would that work?
So it's not known. I think Daniel and Sam are working on it. So if you have, for example, it's open at the moment for one-ended hyperbolic groups whose JSJ has no rigid vertex groups.
I see. Okay.
It's, I think, conjecturally true, but open. And it seems like the symmetry-restricted Leighton's theorem is like would be a useful component that we didn't have when we considered amalgams where there's just one curve.
Mm-hmm.
So I wanted to ask, in your proof, so could you sort of point to the places where you are essentially using the fact that the groups are hyperbolic, closed hyperbolic manifold groups?
Yeah, one key point is right here, where we replace the simplicial complexes with actual manifolds.
I see.
So here, what matters is that once you've done this, you have, in the hyperbolic n space, you have a net that both groups preserve. So for surface groups, if two surface groups preserve the same net in H2, then they have the same volume, so they have to be isomorphic.
I see. I was wondering, I mean, I don't know. For me, this is all pretty new. For instance, if you consider complex hyperbolic manifolds, whether some of these arguments somehow still go through. In fact, maybe there is more rigidity there, who knows?
I think so. We know it holds for any hyperbolic manifold over any field. This theorem.
Ah, it does. I see. Okay, very good. So you just gave us a basic version. Ah, okay. All right. Are there any other questions? Okay, let's thank Emily again. And I think you should get a special prize for finishing early. So let me stop the recording now.